Welcome back to Physics 152 Online. Last time we left off after defining the electric field of a charge or a distribution of charges, we showed how to calculate the force on a charged particle that's in an electric field. And that's given by the equation shown here. If there's an electric field E and there's a charge Q in its vicinity, the force on that charge is just Q times E, remembering, of course, that the charge can be positive or negative. So let's do an example that shows how we would calculate the electric field in a particular region of space and then the force on a charged particle sitting at that point. Here's the example. 3-point charges are fixed on the y-axis as shown in the sketch. There's a positive charge above and below the y-axis and a negative charge at the origin. Find the net electric field at the point P on the x-axis and calculate the acceleration of a particle that had mass m and charge minus 3q sitting at that point. So the way we're going to proceed is to first calculate the electric field at point P. After we do that, it'll be easy to find the force as just Q times the electric field. And to find the electric field, when you're summing up the contributions of different charges, we first want to draw in the fields that each of those three charges produce at point P, sketch them in as vectors, then use any symmetry that's present in the problem to simplify it, find the net components of the field. In this case, the net field at point P could have both an x and a y component, and then we'll be able to write down the net field and then find the field at that point. There must be a little typo there. Okay, so we can see that the positive charge above the x-axis produces a field at point P that would push away from that point, because remember, the electric field is the direction that a positive charge would feel at that point. Similarly, the electric field produced by the positive charge below the x-axis is up and to the right. And so the third point charge at the origin, negative q, would attract a point charge at P, so the electric field would point towards the origin at that point. So we have three vectors that we have to sum up. But we can exploit symmetry in this problem, noticing that the two vectors that are pointing to the right, one above, one below the x-axis, their y components will be equal and opposite to each other, because these two vectors E, since they arise from two equal point charges, will have the same magnitude at that point. So it's easy to see that those two vectors will have y components in their fields that add to 0. And of course, this other field, E2, doesn't even have a y component. So we can, without doing any calculations, we can see that the y component of the net field at point P is equal to 0, and therefore we only have to calculate the x component. And each of these three electric field vectors will have an x component given by its magnitude times the cosine of the angle that it makes with the x-axis. E2 is simple because it's already along the x-axis, so its x component is just minus whatever the electric field is. E above and below, these two e's, we just have to calculate E cos theta and then multiply by 2 because there are two contributions. So the sum of the x components is 2E cos theta minus E2. That's easy to see from the sketch. Now, 2 out in front, what's the magnitude of E? Remember, the point charge gives a field that's k times the charge over the distance squared. So it's kq. The distance is the distance of the dotted line here, and using the Pythagorean theorem we can see what that is. The distance squared is a squared plus 2a quantity squared. Then we multiply by the cos theta. And here's the angle theta that we want to use, but that's also the same angle that's inside the right triangle closer to the origin here. So the cosine of that angle is 2a divided again by the hypotenuse. So 2a over square root of a squared plus 2a squared. And then subtract off E2. E2 is easy to write down because it's just kq over the distance squared, which is 2a quantity squared. And so you'll notice that in the two terms multiplied together here, the quantity in the denominator is the same, except in one case it's to the 1 power, in the other case it's to the 1/2 power. So multiplying those two together gives us that quantity to the 3/2 power. And when we simplify that, we end up with the denominator has 5a squared to the 3/2 power. And then the numerator, of course, we just have 2 times kqa, that sits up there, minus the kq over 4a squared that comes from E2, and then simplifying that gives us a result that has a numerical factor out in front and then kq over a squared. So it's got the right units because k times a charge over a distance squared is the units of electric field, and the minus sign tells us that the overall x component is in the negative direction. So that's our answer. And now all that's left to do is to find the force on the charge minus 3q sitting at point P. We first found the field. Now we can find the force and then the acceleration from that. So E is minus 0.16 kq over a squared in the I hat direction. The force is negative 3q times that, so the minus sign cancels the minus sign that's in the field and gives us a result that's in the positive I hat direction. And then if the particle has mass m, the acceleration is just the force over the mass. So that's a great example of how we first calculate the field, use it to calculate the force, and from the force calculate the acceleration that that charge would experience. There's another example here I'm going to skip over for now, because what I'd like to do now is look at a great application of calculus to the study of electrostatics. And here we want to look at the case where we don't have individual point charges whose electric field we're trying to calculate, but we have a continuous charge distribution. Maybe this represents a piece of matter that we've charged up and it has the charge spread out over its surface. And we want to know what's the electric field due to that whole object that has a smeared out continuous charge distribution at point P outside the object. And what we're going to do is use our expression for Coulomb's law, but write down the differential contribution to the electric field of a differential element of the charge that's on the object. So there's an overall total charge on here, but we break down the charge distribution into tiny little pieces. And then since they're tiny pieces, we can treat them like point charges and write down the expression for the differential contribution to the electric field at a point P. And that's easy to see where that comes from, because for a point charge, E was kq over r squared, right? Here, dE is k dq over r squared. And the r hat tells us that it's in the direction away from that point, because we assume here that we have a positive charge distribution. So we're now going to be able to use calculus for, at least for certain cases where the symmetry is relatively high, we can use calculus to add up the contributions of all of the charge elements by integrating over the entire charge distribution. So that integral would be written down this way. E, remember E is a vector, at point P is the integral of k dq over r squared times r hat. And we're going to be able to write down expressions for dq for certain types of charged objects that will allow us to simplify the integrand and then to carry out the integration process. Remember that the integral is over the entire charge distribution. Now, a little bit of background here. We usually talk about an object that has a continuous charge distribution as having a charge density. For a one-dimensional object, such as a charged rod, that might be a charge per unit length, and we give the symbol lambda for that, not to be confused with the wavelength of a wave. In 2 dimensions, if we have charge spread out over a surface, sigma is the symbol we use to represent the charge per unit area. And similarly, if the object that has charge on it has that charge distributed over an entire volume, rho is equal to the charge per unit volume. We call all of these charge densities, but what's in the denominator depends on the dimension of the object that has the charge on it. Okay, so if we are able to use this lambda, right, and we want to write down the dq that's on a little chunk that has a length dx, along that one-dimensional object, then dq is just lambda times dx, right? Because if we look at lambda, that would be the charge dq over the length dx, and then just solving for dq, that's what we get. And in a similar way, you can write down expressions that would correspond to a charged surface or to a charged volume. Now, here's the example I want to work out because it's a great illustration of how to set the integral up and then how to carry out the integration. Imagine that we have a thin rod of length L that has a uniform linear charge density lambda and that it's a positive charge. We want to find the electric field at a point P on the x-axis. which is at a distance d away from the origin. Now I've showed that this charged rod has some thickness to it just so I can actually make a clear sketch. But we are thinking of this object as lying completely along the x-axis and being essentially one-dimensional. So the geometry's been set up. Here are the steps we follow. We first draw in a charge element dq and label its size and its position. Secondly, we draw in an infinitesimal field vector dE and use the expression for that we get from Coulomb's law, and use any symmetry present to simplify it. Third, we write down an integral for the total electric field and make the appropriate substitutions, for example, quantities like dq that are going to be in the integrand. And the whole goal there is to express the integrand in terms of one variable only. Finally, after we've done the hard work, 1, 2, and 3 are usually the hardest parts. 4, we set up the limits and integrate. And 5, we check the answer for units and for agreement with limiting cases. In this case here, when we're done, we ought to be able to look at what would the answer be if point P were infinitely far away. And if it were infinitely far away, we would expect this rod, even though it has some length to it, to look just like a point charge if we were at a distance away that was very large compared to the size of the object. So there are often limiting cases where we can check our answers. So the first step, draw in a charge element dq, and this little red element you can see, dq, and label its size and position. So it's got a thickness dx, because that's the differential length along the x direction. It's got a position x, measured from the origin, and the distance r, which is going to be in our expression for the electric field, is the distance from the charged element to the point where we're trying to find the field. Secondly, now we can say what the expression is for dE at that point. Clearly it's going to be a vector pointing to the right because this charge is positive. So the starting point, as we wrote down before, is that the differential electric field at point P is k dq over r squared, and r hat in this case will be simple. It will simply be along the I hat direction, because all of these vectors that we add up the contributions of will all have electric fields pointing along the x direction. So, finishing it off, here's where we started before. We wrote down what dE was. We're going to have to substitute in for the dq, and since this is a one-dimensional case, dq, the amount of charge on that little element, is equal to the charge per unit length lambda times dx, which is the length of this element. And then the r that goes into the denominator for the electric field expression, you can tell pretty easily here that that distance r is the distance d minus the distance x. So we write it as d minus x. So look at this. This means our dE expression is now k times lambda dx over the distance d minus x quantity squared, and I said already that r hat is in the I hat direction. So that's the contribution from this little charge element, and that's the hard work. Now we set up the limits and we finish off the problem. So the electric field then is equal to the integral of this quantity summed up starting from x equals negative L over 2 at the left-hand end of the rod and going all the way till x equals positive L over 2 at the right-hand end. Those are the two limits. The integrand we have, it's in the I hat direction. Now this is really easy. It might not be obvious right away, but if you think about it and just do a simple u substitution, you can see that the integral of dx over a constant a minus x quantity squared is simply 1 over a minus x plus an integration constant. So we can use that integral here to rewrite the integral for E as k lambda over d minus x, again in the I hat direction, evaluated between the two limits. When we plug in the two limits and then simplify the problem by getting the two terms over a common denominator, here's the result that we get. And here's the limit, where d is much, much greater than L. So imagine that d, the point P, is really, really far away along the x-axis, where d is much larger than L. Look what happens. But in the denominator, the d squared is much larger than the L over 2 squared. And so this becomes approximately k lambda L over d squared. And take a look, what's lambda L? Lambda is charge per unit length of the rod. L is the length of the rod. So Q is the total charge on the rod itself. And then our answer, kq over the distance d squared, is exactly what we would have if there were a point charge q at the origin. And so that's what we expect. So our answer, not only does it have the correct dimensions, the correct units if we check those out, but it's got the correct expression if we take the limiting case where d gets really large. And that's a helpful way to solve a problem like this and to check your answer. So we'll do another example like this in class, and I hope this has been helpful as an introduction. I'll see you in class.